You ever just stop and, wow, look at your computer? I mean, right now, you might be editing a document, you've got music playing, notifications are popping up from who knows where, and you've probably got a dozen browser tabs open. And it all just works. It feels like your computer is doing 100 things at the exact same time. But how does it actually do that? Seriously, how can a machine with, 8 processor cores handle literally hundreds of different tasks all at once? It feels like it should be impossible, right? Like some kind of digital magic. Well, you're not wrong. The answer is a kind of magic, a really clever illusion that your operating system performs every single second. And to pull back the curtain on this trick, we first have to understand that your computer is basically doing 2 totally different kinds of work. We can think of these 2 types of tasks as the thinker and the waiter. And believe it or not, every single thing your computer does falls into one of these 2 buckets. So on one side, you've got your CPU-bound tasks. These are the thinkers. They're the heavy lifters, the number crunchers. They spend almost all their time maxing out the processor with intense calculations. The only thing holding them back is how fast the CPU can actually think. Then on the other side, we have I/O-bound tasks, the waiters. I/O just stands for input and output, and these tasks spend most of their lives just waiting for you to type something, waiting for a file to load from your hard drive, or waiting for a website to send back information. Their speed has nothing to do with the CPU. It's all about how fast those other things can respond. So what does a thinker task look like in the real world? Well, think of anything that makes your processors sweat. Things like encrypting a file, rendering a 4K video, running a complex scientific simulation, or applying a heavy filter to a photo in Photoshop. All of these need the CPU's pure, undivided attention. And what about a waiter task? Honestly, this is most of what you actually interact with day to day. Your text editor is just sitting there, waiting for you to type. Your web browser spends most of its time waiting for servers across the world to answer its requests. Even huge databases are often just waiting around for the hard drive to spin up and give them some data. They are all, at their core, waiters. Okay, so we have our thinkers and our waiters. To really see why this difference is so incredibly important, let's do a little thought experiment. Imagine a friend asks you to program a game, something like Pac-Man, but for a really old arcade machine that only has a single core processor. Just one brain. Now, for the game to actually feel alive, 3 things kind of need to happen all at once. First, we need to get the player's input from the joystick. That's a classic waiter task, right? It's just waiting for you to move. Next, we have to compute where the ghosts are going to move next based on their rules. That's our thinker task. And finally, we have to actually draw the new positions of everything on the screen, which is another waiter task since it's waiting on the display hardware. So here's the big problem, the absolute showstopper. With only one processor, how on earth do we make these 3 things feel like they're happening at the same time? If we just write the code to run one after another, the whole program gets stuck on step 1. It's just forever waiting for you to move the joystick. The ghosts are frozen like statues, the screen never updates. The game is totally broken. So how do we fix this? How do we unbreak our game? Well, we use the exact same trick your modern computer is using this very second. We create the illusion of doing things at once by juggling them incredibly fast. This is the magic of preemption. It's a fancy term called preemptive multitasking, but the idea is actually pretty simple. Think of the operating system as a super strict, super fast manager. It gives each task a tiny, tiny fraction of a second to run. We call this a time slice. And when that time is up, boom, the OS forcibly pauses or preempts that task and gives another task a turn on the processor. One of the sources I was looking at for this had this perfect analogy. It compared this whole process to a plate spinner at a circus. You know the act. The spinner can't physically touch all the plates at once, so instead they just rush from plate to plate, giving each one just enough of a spin to keep it from crashing down. In our case, the operating system is the plate spinner, and all of our running programs are the plates. And this is what that solution looks like in action. Just look at the timeline. For the first 10 milliseconds, the OS runs the get input task. Then, bam, it yanks it off the CPU and gives the next 10 milliseconds to the compute world task. Then, bam, it switches again, giving 10 milliseconds to render screen. And after just 30 milliseconds, the whole cycle starts over. Again, and again, and again. And that right there is the magic trick. Because this switching happens hundreds, even thousands of times a second, way faster than our brains can possibly perceive. It creates the perfect illusion. It feels like the joystick is responsive, the ghosts are moving intelligently, and the screen is updating smoothly, all at the exact same time. The tasks are running concurrently, but they're not truly running in parallel. But, and you knew there was going to be a but, right? This incredible juggling act isn't free. Every single time the OS switches from one task to another, there's a hidden cost, a tiny bit of overhead that really starts to add up. Think of it like this. You're in the middle of a really deep conversation with a friend, and suddenly your phone rings. You have to tell your friend, hey, hold that thought, remember exactly what you were talking about, then switch your full attention to the phone call. When you hang up, it takes you a second to remember, okay, where were we? That mental saving and loading, that takes time. The CPU has to do the exact same thing. This process has a name. It's called context switching. Before the OS can pause a task, it has to save a complete snapshot of everything that task was doing. What numbers it was working with, where it was in the code, everything. Then it has to load the saved snapshot for the next task. This is the real mechanical work happening behind that multitasking illusion. So what's the actual cost? How much time does this administrative work really take? We'll get this. A single context switch, just one, can take up enough time for your CPU to have executed around 15,000 other instructions. Yeah, 15,000 calculations that just didn't happen, all because the CPU had to play traffic cop. And that brings us to the final and most crucial point. Multitasking is an incredibly delicate balancing act. If the operating system switches between tasks too often, your computer feels super responsive, but it ends up wasting all its power on context switching instead of doing real work. But if it switches too slowly, it's way more efficient, but the whole system feels sluggish and laggy. Modern operating systems are just mind-bogglingly good at walking this tightrope. So that seamless multitasking we take for granted every single day, it's not really multitasking at all. It's a high-speed illusion, a brilliant juggling act of thinkers and waiters, all managed by the OS. And this is just one of the many incredible tricks your devices are performing under the hood. Which kind of makes you wonder, what other invisible illusions are running for you right this very moment?